All right, welcome to The Explainer. Today we are diving into a technology that you've probably seen popping up everywhere in the headlines lately, and that is thorium.
So, is thorium really the future of energy, or is it just a lot of hype? You hear these huge claims, right? That it's this revolutionary power source, it's going to solve everything, and that China has already cracked the code. Well, today we're going to dig in and separate what's real engineering from all that noise.
Okay, so first things first. Let's talk about the promise. What is all this hype about? Why does thorium sound, at least on paper, like the ultimate energy solution we've all been waiting for?
I mean, look at these claims. It's abundant and easy to find. It's supposed to be way safer than uranium. It generates a ton more energy, produces less of that nasty long-lived nuclear waste, and it's hard to turn into a weapon. This list basically reads like a solution to every single problem people have with traditional nuclear power. It sounds incredible, almost too good to be true, right? So, how does it actually work?
All right, now we need to put on our chemistry hats, just for a minute, because this is where it gets really interesting. It's not as simple as just, taking out the uranium fuel rods and plugging in thorium ones. It's a completely different ballgame.
And here's the absolute key thing you have to understand. Thorium itself isn't fissile. That's the fancy word for saying it can't start a chain reaction all by itself. Unlike the uranium we use in most reactors, thorium is what we call fertile. Think of it like a log that's too damp to light on its own. You need to hit it with a blowtorch first to get it going. It needs a little help to become fuel.
So this is how that breeding process works. Step 1, you hit a thorium-232 atom with a neutron. Step 2, it gets unstable and turns into thorium-233. Then, pretty quickly, in about half an hour, it decays into something called protactinium-233. But here's the catch. You have to wait for that to decay again, and that takes about a month, before you get the stuff you can actually use, uranium-233. That 1-month delay, yeah, that's a big deal for the engineers, and we'll circle back to why.
So, here's the bottom line. A thorium reactor isn't really running on thorium. It's actually running on uranium-233, a special kind of uranium that it makes itself from thorium. The thorium is the raw ingredient, but it's the uranium-233 that's actually doing the heavy lifting and producing the power.
Now, because of this whole weird fuel breeding cycle, you can't just cram this stuff into a regular old nuclear reactor. It just wouldn't work well. You need a special kind of machine, a reactor design that's totally different from what we're used to.
And that special machine is the molten salt reactor. So think about conventional reactors, right? They use solid fuel pellets packed into these long rods. It's like a device that runs on massive batteries. When they're spent, you have to shut the whole thing down to change them. The molten salt reactor, though, it's completely different. The fuel is literally dissolved into a hot liquid salt. It's like having a car with the gas tank right in the engine. You can just pour in new fuel and filter out the exhaust while the car is still running. It's a continuous process.
And this liquid fuel idea leads to probably the single biggest safety feature you hear about. I mean, you can't have a meltdown if your fuel is already molten, right? But here's the really clever part. In an emergency, say the power goes out, there's a plug at the bottom of the reactor made of frozen salt. With no power to keep it frozen, it just melts, and gravity does the rest. The liquid fuel drains down into a special cooling tank. The reaction stops instantly, and the whole thing shuts itself down safely. No buttons, no computers, no human intervention needed. It's brilliant.
Okay, so this all sounds amazing. So, what's the catch? Well, this is where the dream runs smack into a brick wall of reality. The biggest challenge with these reactors isn't the nuclear science at all. It's the plumbing.
And I don't just mean any plumbing. We're talking about a hot, radioactive, liquid salt. We're talking 600, 700 degrees Celsius that is just unbelievably corrosive. It just eats metal for lunch. So imagine trying to build pipes and pumps and valves that can handle this stuff day in and day out for years without just dissolving. That right there, finding the right materials, is the monster engineering hurdle.
So, you hear all this news about China's reactor and you think, wow, this is some brand new sci-fi stuff. But here's the craziest part of this whole story. This isn't a new idea, not at all. In fact, this technology has a very long, very forgotten history that started right here in the US.
Yeah, you heard that right. Back in the 1960s, at the Oak Ridge National Laboratory, American scientists pioneered this whole thing. They built a thorium molten salt reactor and successfully ran it for 4 straight years. It worked. So why did it stop? Well, the Cold War happened. The US government decided to pour all its money into uranium reactors because, well, they produce plutonium.
which you need for nuclear bombs. And just like that, the Thorium project was put on a shelf. And now, decades later, China's program got its start by dusting off all that old, declassified American research.
And get this, the big, new reactor in China that everyone is talking about, it's a 2-megawatt research reactor. You know how powerful that US reactor was back in the 60s? 8 megawatts. 4 times more powerful. Now, don't get me wrong, what China is doing is a huge deal. They are advancing the technology. But it's really important to see it for what it is. They're picking up a 60-year-old American idea and finally running with it.
All right, so let's bring this all together. It's time for a reality check. Let's put the hype side by side with the actual engineering facts.
This really lays it all out. The hype says thorium is just safer. The reality? No. The reactor design, the molten salt reactor, is what's safer. You could put uranium in one of those and get the same safety benefits. The hype says it gives you 200 times more energy. The reality? It's probably closer to 5 or 10 times more. Now that's still a huge improvement, but it's not 200. What about less waste? Well, the radioactive profile is different, for sure. But once you add in all the corroded, radioactive plumbing you have to throw away, the total amount of waste you have to deal with is actually pretty comparable.
So you see, the real hurdles left aren't about the nuclear science. We figured that out a long time ago. The hard part now is all engineering. It's things like, how do we create special metal alloys for the pipes that won't get eaten alive? How do we design pumps that can run reliably at 700 degrees Celsius? And maybe the biggest question of all, how do you make this incredibly complex system of creating fuel and processing it cheap enough to actually work on a large scale?
And that's really the big question, isn't it? Is thorium's biggest challenge the science, or is it just about scaling up a 60-year-old idea? The whole journey for thorium energy isn't really about a brand new discovery anymore. It's a question of engineering and whether we can finally solve the tough, practical problems that have kept this amazing idea on the shelf for more than half a century.